So for today's lecture, we'll be doing section 2.4, rational expressions. So for this particular lecture and probably on the next lectures, one of the key concept that we're going to use is factoring. So the topic that we discussed last meeting. Right now, if you are not comfortable doing factoring, please try to practice on your own. You can work on the exercises that I have given you using the module, okay? And also, you can see me during my office hours so we can discuss some things related to factoring or even to this new uh, topic. So, 2.4, rational expressions. So last time when we discussed polynomials, we considered some operations on polynomials, particularly addition and subtraction, and also multiplication of polynomials. So right now, what we're going to do is to consider quotients of polynomials. Okay? So when you have two polynomials and you divide one polynomial by the other, what we will get is actually a rational expression. Okay? So here are some of the examples of rational expressions. So here you have x cubed plus x plus 1 divided by x. So this is a third degree polynomial in the numerator and you have a first degree polynomial on the denominator. So polynomial in the numerator, polynomial on the denominator. In this particular example, you have x squared plus 1 divided by x to the 5 plus 1. So these two guys, we have polynomial in the numerator, polynomial on the denominator. And this third example here, you have x over x cubed minus 1. So again, polynomial over polynomial. Okay? And some more example in here. You have x to the 4 minus x squared plus 1 divided by 4. So in here, in the numerator, you have degree 4 polynomial, while on the denominator, you have a degree 0 polynomial. So constants are polynomials also. So these two here, polynomial over polynomial, this will still give, or this is still a rational expression. But what's so special in this kind of example? This tells us that any polynomial is actually a rational expression. Because if you have a polynomial, everything is divided by 1. So you have a quotient of two polynomials. Okay? And therefore, you have a rational expression. So every polynomial is a rational expression. Okay? And for this example, you have now polynomials with two variables. So x squared y all over x minus y squared. So this is still a rational expression, but this time you have two variables. Okay? So, as I have mentioned, what we will be using mostly in the next concept that we will discuss is factoring. So, our goal when we have a rational expression is to simplify it. Okay? We want to simplify rational expression. That is our main goal. Whether you add or subtract or multiply or divide rational expressions, okay, our main goal is to simplify it. And that factoring is will play a very important role. Okay, so let p of x over q of x be a rational expression in one variable. Okay, now the polynomial p of x is called numerator And the polynomial q of x is called denominator. It's the same terminology that we are using for fractions, okay? Numerator and denominator. If the polynomials p of x and q of x do not contain common factors, okay, except for 1 and -1, we say that the rational expression is reduced to lowest terms or simplified. Okay? So if we are given a rational expression, this is what we want to do. We want to reduce it to its lowest terms, or we want to simplify it, meaning the numerator and denominator must not contain common factors except for 1 and -1. Okay? Now, same definitions are used if P or Q are polynomials in 2 or more variables. Okay? So, most of the time we will be discussing one variable, but there will be some rare times where we will include 2 or more variables. Okay? Just like before. So, when dealing with rational expressions, one assumes that the denominator does not take the value 0. Okay? Just like in the rational numbers, we don't want the denominator to be 0 because it's undefined. Or if you are dividing two numbers, you don't want your divisor to be 0. Okay? But here we are looking at rational expressions in one variable or two or more variables. So the variables can assume some number, and therefore the denominator we will assume some number. So we don't want that number in the denominator to be 0. Okay? In particular, given the rational expression p of x over q of x in one variable x, one only considers x for which q of x is not equal to 0. Okay? So meaning you can replace x with anything. Okay? We can replace x with anything except for those x's that will give q of x equals 0. Okay? So we only consider x for which q of x not equal to 0. And as a preview, or as a preview, we call the set of all x for which q of x not equal to 0 the domain of p of x over q of x. So I am now introducing this particular term, domain of p of x over q of x. And we will be discussing more about domain when we start dealing with what we call functions. Okay? So, as I mentioned, our goal is to simplify rational expressions. Okay? Let us recall the following. In the set of real numbers, the following cancellation property holds. So you have a times c divided by b times c. This is equal to a over b, provided that this c here is not equal to 0. And of course, the b must not also be equal to 0. Okay? So meaning you can cancel out a factor in the numerator with the same in the denominator, provided that they are not equal to 0 or it is not equal to 0. Okay? Now, to simplify rational expressions, one cancels out factors common to both numerator and denominator. Just like this, we cancel the c because it's a common factor in both numerator and denominator. Of course, here, excluding 1 and -1, since we will be dealing with expressions with one variable. Okay? So we exclude this 1 and -1. Okay? So let us consider this first example. We have x squared plus 6x plus 9 divided by 12 plus x minus x squared. Okay, so copy that and work on your own paper. and then I will show you the solution of the record. Now, let us consider this next example. So simplify x squared minus 1 all over x cubed minus 1. So for this next example, we have to simplify x cubed plus x all over x to the 4 minus 1. Now, what we just did was to simplify rational expression. Okay, rational expressions. We just simplified given rational expressions. But let us make it more complicated. What we're going to do is to get two rational expressions and operate on them. Okay, so we multiply or divide rational expressions. We will also add and divide or add and subtract rational expressions. And we will start with multiplication and division of rational expressions because this is much easier compared to addition and subtraction of rational expressions. Okay, so we recall this multiplication of fractions in the set of real numbers. You have a over b times c over d. All you need to do is to multiply the numerators and multiply the denominators. And those will be the numerator and denominator respectively of the product. So this guy here will be equal to AC divided by BD. And of course, we are assuming that B is not equal to 0 and D is not equal to 0. Okay, so this is multiplication. For the division, look at this. You have A over B all over C over D. Okay, so there are a lot of bars in here. Okay, now I want to tell you that this long bar here will always be emphasized when you have um, division of rational expressions. Okay, meaning this long bar here. Okay, the expressions above it, if it is a rational expression, let us just call it the big numerator. Okay, and then the expressions below that long bar, let us just call it the big denominator. Okay, of course, this rational expression here has its own numerator and denominator. And then this rational expression here has its own numerator and denominator. So I am going to add that adjective big to emphasize that it is the numerator of the outermost division sign, which is this guy here, the long bar. Okay, so if we divide A over B divided by C over D, we can convert this to multiplication, but we need to get the reciprocal of the big denominator. Okay, so this guy here, A over B divided by C over D will be equal to A over B times D over C. Okay, so your big denominator here, okay, we get the reciprocal. Okay, and then we change now to multiplication. And of course, this is the definition of the multiplication. Okay, and furthermore, we will assume B is not equal to 0 because it is a denominator of A over B. D is not equal to 0 because it is a denominator of C over D. And C is not equal to 0 because if C is equal to 0, then the big denominator will be 0. Okay? Unless the denominator D is also 0. So it will be undefined. So look at those conditions. Okay? So this is the same thing that we are going to use when multiplying, dividing rational expressions. Here we have real numbers, okay? And in rational expressions, we will use the same formulas, okay? But here, I want you to take note of the following. It is helpful to write each expression in factored form so that the common factors can be cancelled. Actually, if you wrote all the expressions in factored form, you will see immediately all the common expressions or the common factors. Okay? Okay? Also, always leave the final answer in factored form. So don't multiply those factors if they can be multiplied. You don't need to multiply that because when you multiply them, you can get some errors in the multiplication and that will give you uh, some little deductions, possibly. Okay? So our first example here, okay, look at the instruction. Perform the indicated operations and simplify. So leave the final answer in factored form. So we have 3x plus 6 all over 5x squared times x over x squared minus 4. Okay, so again, we will work on the example. We will write out the solution of the record. So you may start copying or pausing this. So for the next example, here we have division. So you have 6x over x squared minus 4. And then you have that longer line here. So this is the outer division. Okay, so divided by 3x minus 9 over 2x plus 4. Okay, so again, hit pause. So for the next example, we have the following. So x squared plus 7x plus 6 over x squared plus x minus 6 all over x squared plus 5x minus 6 over x squared plus 5x plus 6. So again, we want to simplify this and look at that emphasis. This is a longer line compared to this line here and this line here. So this longer line tells you that's the outermost operator. So you have a rational expression in the big numerator and another rational expression in the big denominator. Okay? So again, work on the example. So I mentioned we started with multiplication and division because they are much easier um, to operate with. Okay? Compared to these next concepts or next topics. So addition and subtraction of rational expressions. Okay? So let us recall again the ways of adding and subtracting rational expressions in the sense of real numbers. Okay? So in here you have a over b plus c over b. Observe, you have the same denominator. So you just copy the denominator for the sum. And the numerators, or the numerator of the sum, you just add the numerators here. So a over b plus c over b, it's equal to a plus c over b. Okay? Same is true with the subtraction. So if you have minus, you just replace the plus with the minus here. Same denominator. Okay, same denominator, so you just copy the denominator here and just add or subtract whatever the numerator is or are. Okay? And then there's a possibility that you don't need to simplify. Okay? And also there's possibility that you have to simplify after addition and subtraction. Okay? This is the more complicated one. you have two fractions with different denominators. You add and subtract them. Okay? So in here, you have A over B plus C over D. So what do we do with this? The denominator of the sum will be the product of the denominators. Okay? So the denominator of the sum will be the product of the denominators. So you have BD there. For the numerator of the sum, you cross multiply. The numerator of the first addend will be multiplied to the denominator of the second addend. And then the numerator of the second addend will be multiplied to the denominator of the first addend. So you cross multiply. Okay, so A over B plus C over D, this is equal to AD plus BC all over BD. Okay, all over BD. Okay, for the subtraction, of course, the same thing except that you now have minus. So A over B minus C over D, this is equal to AD minus BC all over BD. Okay? Now, to see this easily, or for you to remember this easily, you have your A over B plus C over D. You want to have the same denominator. You want to have the same denominator, so you can apply this expression here. Okay? So you have a denominator B here. You have a denominator D here. Okay? So let me rewrite that again. So A and then over B, and then here plus you have your C over D. So one of the ways to have the same denominator is to copy the denominator of the other expression and put it also as one of the factors in the denominator. Okay? For example, you have here B and there's a D there. We can put D here. Okay? But if we put a D on this denominator, you have to put a D in the numerator. So you are not changing the original expression A over B. So I placed D here. I have to put D also in here. Now, for this guy, you already have the D, the missing part, the missing denominator B. We multiply it with the D. So here, D, we put that B, okay? And then since I put a B on the denominator, we should also put a B in the numerator. Okay? Now notice, as I have mentioned before, AB equals BA. Okay, AB equals BA. So BD, it's the same as DB. Okay, so BD and DB, they are equal. Meaning we can use this expression here. We can use this formula here, I mean. Okay, so this one, the same denominator. Therefore, you can just copy the denominator, BD. And then from here, you just add the numerators. So you have your AD plus CB. And you can use, again, this guy here to get your BC. Okay? Are we good?
Yeah.
Okay. Thank you. So let us work on these examples. So we have the first example in here. Okay. So I'll hit pause again. So for the next example, you have 2x minus 3 over x minus 1 minus 2x plus 1 over x plus 1. So in here, you have now different denominators. So this is more complicated than the previous example. Okay, so let us work on this. So for our next example, you have x over x squared minus 4 plus 1 over x. Now, we will do addition and subtraction with the use of least common multiple. And this least common multiple, it's the same concept that you know when you had discussed this in your primary school, possibly, okay, or early years of the secondary school. Least common multiple, okay? So, given two polynomials p of x and q of x, their least common multiple, or LCM, is a polynomial of least degree that has each polynomial as a factor. Okay? To find the LCM of the two polynomials, step 1 is we factor out or we factor each polynomial. So we factor q of x and p of x. Okay? Then the LCM is the product of each of these factors raised to a power equal to the greatest number of times that the factor occurs in all of the polynomials. It's a long statement, but let me try to explain it using an example or using a couple of examples here. Okay? For example, your p of x equals x squared minus 1. And your q of x, it's x squared plus 2x plus 1. The factored form of x squared minus 1, it's x plus 1, x minus 1. The factored form of x squared plus 2x plus 1, it's x plus 1 squared. Okay? So the factors that we see here, for p of x, you have x plus 1 and also x minus 1. The factor q of x, or the expression q of x, the factor that we see here, it's x plus 1. And it is being raised to the power 2. But the factor, it's just x plus 1. Okay? If you remember, you have something is a factor of multiplicity 2. Okay? So this guy here, x plus 1 is a factor of q of x with multiplicity 2 because you have x plus 1 squared and that will give you your q of x. So the exponent that we see here tells you the multiplicity of the factor x plus 1. So let me write that. So multiplicity 2. Meaning x plus 1 appeared twice as a factor of q of x. Okay? So, you have your x plus 1, x minus 1, and x plus 1. So, the LCM of P and Q, okay? LCM of P of x and Q of x will be the product of all the factors that we see. Okay? You have x plus 1 in here, you have x minus 1, and again, x plus 1 appeared. So you'll just write x plus 1 once for this. So you have your x plus 1, and then x minus 1. But according to this, look at this. LCM is the product of each of these factors. So x plus 1, x minus 1, and x plus 1. These are the factors. That's what we are talking about for this part. Now, look at this. Raised to a power equal to the greatest number of times. Okay? Raised to a power equal to the greatest number of times that the factor occurs in all of the polynomials. So what is this? X plus 1 occurs once in P of x. X minus 1 occurs 1 in P of x. X plus 1 multiplicity 2 here. So x plus 1 occurs twice for Q of x. So we use that power. Okay, we use that power. So raised to a power equal to the greatest number of times. So meaning, we use 2 in here. Okay? We only use x minus 1 raised to power 1 because x minus 1 appeared, but the highest power that we see in x minus 1, it's just 1. So you only have this x minus 1. Okay? Therefore, this is your LCM. So LCM of P of x and Q of x is x plus 1 squared x minus 1. Okay? Let's have this another example here. So P of x and Q of x, they are all in factored form. You have now x plus 2 squared, x minus 2, 2, sorry, for P of x, it's x times x plus 2 squared times x minus 2. For Q of x, you have 2 times x plus 2, x minus 2 to the 4th power. Okay? So for P of x, in this example, P of x factors are, you have your x, you have your x plus 2, but it appeared twice. So multiplicity 2. And then the other factor, x minus 2. So x plus 2, multiplicity 2, because it appeared twice there, and then x minus 2. For the Q of x, the factors are, you have 2 for this, you have x plus 2, it only appeared once, okay? And then you have your x minus 2, multiplicity, so multiplicity 4, because that's to the 4th power. Okay? So, what is the LCM of P and Q? So, LCM of P of x and Q of x. So, you multiply all of those factors. So, you have your 2, you have your x, you have your x plus 2, and you have your x minus 2. Those are all the factors that appeared. X plus 2, x minus 2. And then here, the 2, x plus 2, and x minus 2. Now, x, the highest power that we see in x, it's just 1 from P of x. Okay? The 2, the highest power that we see for 2, that's also 1. That's from Q of x. Now, the x plus 2, you have power 2 from P of x, and then power 1 from Q of x. So the highest power that we see, it's 2. So x plus 2 here will be raised to the power 2. x plus 2 here will be raised to the power 2 because that's the higher power. And then for the x minus 2, from p of x minus 2 has power 1. From q of x minus 2 has power 4. So the higher power that we see here, it's 4. So for this, we write to the power 4. Okay? So that's the LCM for P of x and Q of x. So again, the LCM is the product of each of these factors. So these are the factors: x, x plus 2, x minus 2, and 2. X plus 2 already appeared from P. X minus 2 also appeared from P. So I do not have to repeat that. Okay? So the product of each of these factors raised to a power equal to the greatest number of times that the factor occurs in all of each polynomial, or in all of the polynomials. Okay? X plus 2 here appeared in P. X plus 2 also appeared in Q. But the higher power is 2. That's why we have a 2 here. X minus 2 appeared in P. X minus 2 also appeared in Q. The highest power that we see is 4. That's why we have 4. X only appeared in P. So we just use that X. And the highest power for X, it's 1. That's why you have 2 to the 1, or X to the 1 here, or just X. 2 appeared in Q only. So we write that 2. And the highest power for 2, it's also 1. That's why this is just 2 to the 1, or simply 2. So you have this. The LCM of P of x and Q of x is 2x, x plus 2 squared, x minus 2 to the 4th power. Okay? Question on how to get LCM. So, what we're going to do is to use this concept of LCM in simplifying rational expressions, or simplifying the sum or difference of rational expressions. The LCM method, okay? So rational expressions can be added or subtracted using LCM method. This is helpful when the denominators of the rational expressions have common factors. So in the previous examples that we had, the denominators do not have common factors. Okay? So in the next examples that we will discuss, that we will answer, some of them have common factors. Okay? So LCM method for adding or subtracting rational expressions. Find the LCM of the denominators. We call them the LCD, least common denominator. Okay? Write each rational expression using the LCM as the common denominator. Okay? So write each rational expression using the LCM as the common denominator. Since all the expressions have the same denominators, add or subtract using the usual way. Because once you have your common denominator, they have the same denominator. That's why it's common. Okay? And remember when I tried to do this, you have your A over B plus or minus C over D. What we did here is to do A D over BD plus CB over DB. What we actually did here is finding a common denominator. BD is a common denominator. So if you put some expression in the denominator, you have to put the same expression in the numerator. Okay? Okay? And then we can add these two guys here the usual way. Okay? So let us look at this first example. Okay? So let us now look at this next example. X over x minus 1 squared plus 2 over x minus x plus 1 over x cubed minus x squared. Okay? So for this example, let me do it on the record. Okay? So, let us wait a bit. It's not appearing in your screen. So we copy the expressions first. You have x over x minus 1 squared plus 2 over x minus x plus 1 over x cubed minus x squared. So first, this x cubed minus x squared can be factored into x squared times x minus 1. Okay? So you have x cubed minus x squared. X squared is a common factor. So we factor out x squared, and what's left inside would be x minus 1. Now, look at all the factors. You have x minus 1 squared here. You have x squared, and then you have x minus 1. Okay? So what is the LCM? So we have three expressions here. So let's say this is P of x, this is Q of x, and this is R of x. Okay? So P of x, factors of P of x, it's just x minus 1, but with multiplicity, let me shorten this as multiplicity 2, right? So x minus 1 squared. So x minus 1 multiplicity 2. For the Q of x, we just have x here. So we just have x. For the R of x, okay, let us put that. We have R of x. We have x, but x has multiplicity 2 because you have x squared there. And we have x minus 1. Okay? So what is now the LCM? So LCM of P, Q, R. So we multiply all the factors that appeared in this. So you have your x minus 1, you have x. Here also you have x and also x minus 1. So you have your x and x minus 1. Okay? But what is the highest power of x that appeared? This has power 1. This has power 2. So power 2. Okay? So power 1 here, power 2 here. So the highest power is 2. So we use x squared. We put x squared for the LCM. And then for the x minus 1, we have power 2 in here. So multiplicity 2. Here we just have power 1. So we use power 2. So you have this power 2. So this will be the LCD. X squared times x minus 1 squared. Okay? So, what are we going to do with these guys? With these expressions or with this expression? We insert the missing to each of these expressions here. Okay? So you have x minus 1 squared. For this, we are missing the x squared. Okay? So we insert the x squared here. Of course, we put x squared above. For this guy, you have x. What are we missing? We are missing one of the x's because this is x squared. We only have x here. So we have to put 1x, and we have to put x minus 1 squared because it's also missing there. Okay? For this, you have x squared, x minus 1. We already have the x squared. We only have one x minus 1 in here, but we need power 2. So we will insert x minus 1 here. And of course, put x minus 1 also in the numerator. So all in all, this is what happened. So let me write again that LCM. So LCM, it's x squared, x minus 1 squared. So in this guy, we are missing x squared. So we put that. In this guy, we are missing x times x minus 1 squared. So we put that. And then for this guy, we are missing x minus 1. So we put that. Okay? Now, all of them have the same denominators. So all we need to do now is to add or subtract the numerators. And then simplify if possible. Okay? So if you do that, this guy here, x times x squared, that becomes x cubed. Here you have 2x. That's your 2x times x minus 1 squared. So x minus 1 squared, that's 2x squared minus 2x plus 1. And then you have the minus here, minus here. Then you multiply these two. X minus 1, x plus 1. You have x squared minus 1. And you can multiply these two expressions here. So 2x times this expression. And then you distribute this minus here. Okay? So if you do that, you will have this. So x cubed is it still here? Here you have 2x times x squared. That's why you have 2x cubed. Then here you have 2x times negative 2x. That's why you have minus 4x squared. Then you have 2x times 1. So that's why you have 2x in here. Are we good? And then here you have x, oh, you have minus x squared. That's why you have minus x squared here. Then minus times negative 1 in here. That's why you have plus 1 in here. Okay? And then we just simplify the numerator. So if we simplify that, you will have this. 3x cubed minus 5x squared plus 2x plus 1. Okay? Now, let me say that the numerator is prime. You cannot factor this. Okay? So we will have this as our final answer. Okay? So, what we're going to consider now are what we call complex rational expressions. Okay? So by complex rational expressions, we only mean that your numerator is a rational expression, your denominator is also a rational expression. And possibly your numerator is not just a rational expression, but a sum of polynomials and rational expression. Your denominator may also be a sum of polynomials or rational expression. So complex. Okay? So if the numerator or denominator of a quotient involves rational expressions, then the quotient is called a complex rational expression. Okay? For example, here you have 2 plus x over x plus 1 all over 1 minus x plus 2 over x plus 1. So numerator, it's a rational expression. It's a sum of polynomial and a rational expression. Denominator is the same. So this whole guy here is a complex rational expression. Same is true with this. You have x squared over x squared minus 1 plus x all over 3 minus 4 over x minus 1. So complex rational expressions. Of course, our goal is to simplify these complex rational expressions. Okay? So when simplifying a complex rational expression, one may use any of the following two ways. First option, we treat the numerator and denominator of the complex rational expression separately. Okay? Performing whatever operations are indicated and simplifying the results. Then we follow this by simplifying the resulting rational expressions. So you have a big numerator, simplify it. You have a big denominator, simplify it. And then now you have possibly a simpler rational expressions compared to the original. Then you simplify that. That's your first option. Second option is by the use of LCM or LCD. So find the LCM of the denominators of all the rational expressions that appear in the complex rational expression. Then we multiply the big denominator and big numerator by the LCM and then simplify the results. Okay? Simplify the results. So I will show both options. Okay, in the next example, I will present solutions with the use of option 1 and option 2. And then it's up to you which option you would prefer to use. Okay? But again, I will show the solutions of the record. So let me show you this first example. So we want to simplify 2 plus x over x plus 1 all over 1 minus x plus 2x plus 1. This is our last example for the lecture today. We want to simplify x squared over x squared minus 1 plus x all over 3 minus 4 over x minus 1. So that's the end for the lecture today, and thank you for joining me here.